Have you ever just looked around at the world? I mean, really looked at it, with all its incredibly messy human interactions, wildly volatile economies, and super complex machines, and wondered, is there a hidden code behind all of this? Well, welcome to today's Explainer, where we're going to explore the math of everything. We're diving into this absolutely fascinating idea that our seemingly chaotic universe can actually be completely deciphered through a single, unified mathematical language. We're going fundamentally deep today, looking at how the exact same math that lands a rocket on a dime could also explain your own fickle, everyday decisions. And ultimately, we'll see how mastering this very math is literally the final frontier for artificial intelligence.
All right, so here's our roadmap for this explainer. First, we'll look at the 6 lenses to see the world. Second, how AI thinks. Third, the human brain's prediction and fickleness. Fourth, uncertainty and political preferences. And finally, completing AGI.
Okay, kicking things off with part 1, 6 lenses to see the world. Now, whether you're an engineer building a self-driving car or an economist trying to stabilize runaway inflation, you absolutely have to look at the world through these 6 objective mathematical lenses. First up, we have states. This is the hidden essence or true underlying condition of a system. Second are policies or controls. These are the actual interventions or actions we take to physically change that system. Third, measurements, the imperfect external signals we actually get to see in the real world. Fourth, parameters, the structural weights or the built-in rules of the system. Fifth, distributions, the probability structures that essentially map out our uncertainty. And finally, errors and noises, those random, totally unpredictable fluctuations that just mess with our plans. Literally everything in our uncertain world boils down to these 6 variables.
So what do we do with them? We run those 6 variables through a continuous optimization flow. It's kind of like a giant puzzle. We take messy, noisy, real-world data and run it through what's called a Kalman filter to strip away all that static and noise. Then we use Markov chains to logically link our current states to future states. And finally, we use Bayesian inference to constantly update our beliefs the second new evidence comes in. All these tools just beautifully flow together, turning raw, chaotic data into highly actionable predictions and optimal paths of control.
Moving right along to part 2, how does AI think?
Now, check out the sharp contrast between these 2 types of AI. On one hand, you have generative AI, like large language models. These guys map human thought into language vectors. They use gradient descent to minimize errors and basically hunt for the maximum likelihood of what the next word should be, based purely on statistical correlations. But on the other hand, look at physical AI, like autonomous drones. They actually interact with the objective laws of reality. They use Bellman equations and reinforcement learning, which is pure optimal control theory, to constantly measure their physical state and adjust their actions in the real world. It's a completely different ballgame.
Which brings us to part 3, the human brain's prediction and fickleness.
So here is where our story gets really interesting, because human brains actually process information a whole lot like machines do. Mathematically speaking, your brain operates incredibly similarly to an extended Kalman filter combined with constant Bayesian updating. Think about it. You walk into a room, you take in imperfect sensory measurements, you automatically filter out the noise, and you update your assumptions. You're constantly minimizing prediction errors without even trying. But, and this is a massive but, we humans do not operate in a purely objective vacuum the way a robot does.
And that brings us to absolutely crucial concept of endogenous noise. I really want to slow down for a second here. Physical laws, like gravity or thermodynamics, they don't care about your feelings, right? They are purely objective. But human economic and social systems, they are almost entirely driven by unpredictable human fickleness. Our emotions, our cognitive biases, our tendency to just change our minds on a whim. This creates endogenous noise, which is essentially random noise generated from inside the system itself.
Let's dive into part 4, uncertainty and political preferences. So, if humans are so incredibly fickle, how on earth do we mathematically model this subjective human noise at a macro level? Well, we turn to a really vital piece of research by Seung-Rae Kim from 2004, titled Uncertainty, Political Preferences, and Stabilization. Honestly, this paper is the missing puzzle piece. It takes these massive mathematical models of an entire economy, called dynamic computable general equilibrium models, and literally merges them with optimal control theory. Crucially, Kim's work figures out how to explicitly inject human political biases right into the strict math. It mathematically answers exactly what happens to an economy when a government has subjective, explicit policy preferences.
In Kim's model,
We get to see exactly what happens when an economy gets shocked. If a government acts entirely neutral, it applies policy one way. But what if that government has a strong, built-in political preference for, let's say, clean industries over dirty, polluting ones? The math shows that the optimal macroeconomic stabilization path drastically changes based entirely on that political bias. The government might spend way more vigorously on clean goods and aggressively restrict dirty ones, which completely alters the speed and shape of the economic recovery. The math perfectly captures the human bias.
And building right on top of that, when the underlying parameters of the economy become highly uncertain, meaning policymakers really aren't sure how their actions will ripple out into the real world, the math literally forces them to adjust their controls. As that additive noise and uncertainty crank up, the mathematical models dictate a much flatter, far more cautious use of policy variables. I mean, it makes sense, right? You can't just slam your foot on the gas pedal if you have no idea how the car is going to react.
Finally, Part 5, the key to completing AGI.
So, how does this obscure macroeconomic control theory connect back to the future of AI? Well, we often tend to think of AGI, artificial general intelligence, as just endless, mind-boggling processing power. But true AGI won't just be about raw computing. In the AI era, the ultimate key is going to be how well a system can integrate human and socioeconomic rules on top of physical laws, baking them directly into the stochastic control processes of an incredibly uncertain real world. To truly work, AGI must mathematically digest our human fickleness, our cognitive biases, and those complex government political preferences. It has to move way beyond just basic physics and grammar, and master the probability models of our own capriciousness.
Which really leaves us with one final, profound thought to chew on. If researchers can actually figure out how to program our deeply endogenous noise and our political biases right into an optimal control flow, we might literally witness the birth of true AGI. But it begs the question, can a machine ever truly calculate the completely unpredictable math of the human heart? Thanks for joining me on this explainer. We'll see you next time.